Hello and welcome to this OnePLM webinar on 5-axis and multi-axis CAM. My name is Michael Smith and I'm part of the OnePLM marketing team, and I thank you very much for joining us today. I'll be joined on today's call by my colleagues Lee Adamson and Mark Fitt. I want to quickly run through some rules for the call, as well as give you some background on who OnePLM are. The first thing to mention is that everybody is on mute, and the reason for that is so we can work through today's content with no stopping. It's worth mentioning that we are taking questions throughout the entire call, and you can enter your questions using the Q&A window or the chat window you'll see on your screens. And if we get time towards the end, we'll try and answer as many questions as we can, if there are any left over to answer. Our team are live on the call, and we will be answering as many questions as we can on these chat windows throughout the call. So there's no limit on how many questions you can ask. You can ask as many as you want, and we'll try and get back to you as soon as we can. And if for any reason we don't have time to answer your question on today's call, then rest assured we will follow up with you on email and calls after today's webinar. Today's session will also be recorded, so you will receive an on-demand version of today's webinar very shortly. And finally, if you have any issues at all with audio or visual during today's call, then please do let us know with the chat windows. We're available to help with any kind of technical issues you may have, and we want to try and make sure that your experience is as smooth as possible, so please do let us know. Now on to who we are at OnePLM. Where OnePLM really adds value is to help companies embrace digitalization by using our experience and ability to take away the mystery from powerful software applications. And we do take a genuine satisfaction across the company from seeing our clients get tangible business benefits from the software we supply and the services we offer. And as a team, we have a lot of experience. Founded in 1997, over time we've managed to build a client base of around 1,500 companies, and this equates to around 20,000 users. And we are a platinum partner in the UK with around 85 staff spread across 2 offices in Aynsham and Liverpool. I'm now going to pass you over to Lee, who's going to take you through the introduction of the webinar. And if you do want to communicate with us, as I said before, please do use the chat window or the Q&A window, and we'll be in touch as soon as we can. Over to you, Lee.
Thanks, Michael, for the introduction. Hello, everyone, and a warm welcome on today's webinar looking at 5-axis and multi-axis machining for NX CAM and Solid Edge CAM Pro. It's great to see so many people have registered and attended today, and we hope you have a good insight from this event. I'd like to introduce myself. I'm Lee Adamson. I'm Business Development Manager for Manufacturing here at OnePLM, so I look after the Siemens portfolio of products for CAM. Also joining me today is Mark Fitt from our technical team. He'll be taking us through this webinar in more detail shortly. So let's have a look at the agenda. And without stealing Mark's thunder, just a quick run through of what we'll be looking at today. Firstly, we'll be looking at multi-axis roughing and 5-axis adaptive roughing. We'll then look at some 5-axis toolpath using guiding curves. Moving on from there, we'll look at some high-performance barrel tool machining, automatic 3 to 5-axis tilt tool techniques. We'll then look at port tube machining, 5-axis and turbo machinery. And then finally, we'll look at merged toolpaths functionality. So I hope you can enjoy today, and I'll now pass you over to Mark.
Thank you, Lee, and once again, welcome to OnePLM's multi-axis machining webinar. So we've all seen that the manufacturers are quickly adjusting to the new market trends. To stay competitive, they are making significant investments in the latest hardware and software technologies. Sophisticated multifunction CNC equipment, high-speed machining and toolpath verification are some of the biggest impact investments in the last 3 years. Today we'll talk about one of these technologies, 5-axis or multi-axis machining. You'll learn about the latest developments in this area and how you can utilise this technology to run a more efficient machining business. Manufacturers are increasingly using 5-axis machining because it provides powerful advantages. You can produce complex parts with fewer operations and setups. In many cases, you can reduce machining time, improve tool life, and also improve part quality. Consequently, this helps you cut production costs and deliver parts faster. 5-axis machining is typically used for manufacturing complex parts with challenging geometry, such as aircraft structures and engine components. As the complexity of different parts has been increasing, 5-axis machining has been used for a much wider range of parts, including mould and die and medical. The machining process can be quite challenging. The simultaneous 5-axis operations are performed on high-performance machine tools. Maximising machine uptime and avoiding collisions are critical for these operations. So as well as the aerospace industry, multi-axis machining is now being used in many other industries, including medical, energy and automotive sectors. To effectively program 5-axis jobs, you need a set of advanced tools in your CAM system. Most importantly, you need to have full control of every aspect of the machining process, especially the tool axis. Ease of use and minimising manual input to create these complex operations can help you be more productive. Having specialised programming operations for specific operations, such as blisk and impeller machining or port machining, can be critical. Using standard generic 5-axis functions to program these types of parts can be time-consuming and can be prone to errors. Also, for seamless transition to 5-axis machining, advanced CAM software should also have capabilities to automatically convert 3-axis operations into full 5-axis operations. Collision-free, of course. First of all, let's look at multi-axis roughing. When machining a part, the goal is to remove material as fast as possible. Most of it's done in the roughing operation. When dealing with mould and prismatic shapes, the fastest way to do this is using our high-speed adaptive milling roughing cycle. With this type of toolpath technique, you can cut curved floors and other complex shaped pockets and features in simultaneous 5-axis mode. This allows for added flexibility to mill around these complex shapes and minimise follow-up operations to clean up any remaining material. It utilises the latest adaptive milling techniques of controlling step over, cut depth and chip thickness to employ high feeds and speeds. So let's take a look at this in NX. So I've got this multi-axis part, it's got some curved floors, some curved profiles, and we're going to look at how we can quickly rough this out in a multi-axis mode. I'm just going to temporarily hide the machine so we can look at the toolpath in a little bit more detail. So here's the multi-axis roughing operation. If I just go in to have a look inside that operation, there are some things that are worth pointing out. We can specify a drive floor and calculate the depth mode from that floor, or we can define a drive ceiling and define the depth mode from that ceiling, or in this case I've defined both and we're going to interpolate between the two. If we just quickly look in my layers, you can see that I've created just a simple curved surface as the drive ceiling and a surface as the drive floor. I'm using the adaptive cut type and I've defined the cut depth and step over and so on based on the requirements of the operation. If we just verify this, you can see that if I quickly just press play, you can see that this is a true simultaneous 5-axis operation. The tool axis is indeed changing angle all the time, and this is being driven automatically by the operation. I didn't have to put any tool axis vectors in or anything like that. I mentioned earlier that one of the big necessities of multi-axis machining is the ability to simulate the G&M code offline before you send it out to the shop floor onto the real machine. I'm going to just switch the machine back on, and then I'm going to go into NX's simulate machine function. This is built inside of NX. This is standard in NX nowadays. I go into Simulate Machine. So you can see that the program has been post-processed in the background, and this is the detail in this window. We can also see that we can also have other windows open, such as machine status, which shows us the tool axis positions, highlights if we're going to get any software or sort of soft limit errors, that type of thing. Okay, so I'm going to switch on the material removal, and I'm going to simply play this, and we'll see the true G&M code simulation. You can see I've got the display tool trays switched on. I can switch that off. I can show the whole toolpath if I choose to, or I can just have it showing the material removal simulation. Let's just speed that up a fraction. This is based on the feed rates specified in the G&M code. So we'll speed that up so we can just see what's happening. Now in the background, NX is checking for obviously collisions. It's checking for gouges of the work part, and you can either get the simulation to stop when it sees a collision or a gouge and highlight that, or you can just get it to output a report at the end of the simulation for you to analyse and obviously make amendments if needed. So as I say, this type of inbuilt G&M code inside of NX is essential for proving out these complicated multi-axis type toolpaths. Okay, let's stop that and let's finish and go back into standard NX CAM. The next method I want to talk about is a 5-axis finishing operation that we call guiding curves. This is a powerful operation that will let you create a 5-axis toolpath directly onto the machining area with full control of the toolpath flow. It does this by selecting a curve or multiple curves that will guide the toolpath on the selected machining area. So no more creating projection surfaces in the CAD. No more trying to figure out which direction to project the toolpath onto the machining area. These are all things of the past with this new operation. You have access to full tool axis control, whether you want to stay normal to the surface, interpolate between several tool axes, lock some axis, etc, etc. Also, just a quick note on the tool axis, it's not just about putting vectors onto the part and running it on the machine. You also need to have proper control over the smoothing as the tool axis goes from one position to the next. So here I've got a sort of mill turn type scenario. So we might be looking at this on a mill turn type machine, and we want to machine the surfaces in the middle of the part there using a multi-axis toolpath. So I've created a variable axis guiding curve operation, and if I just go into that to have a look at that, you can see it's showing the toolpath. I can switch that on or off as needed. I've defined the cut area. This is the area that I want to cut. No other surfaces needed, no projection surfaces, nothing like that. I've also, in this case, defined 4 guiding curves. As I said, it could be a single guiding curve or multiple. And these will dictate the flow of the toolpath from one end of the cut area to the other. I've defined a helical cut pattern to keep the tool fully engaged on the part, and obviously the direction of cut and the cut order are also been defined. So let's verify that just to have a look at what's happening. And if we go into the replay mode and just press play, you can see this is a fairly straightforward operation. You can see, just as a point, I'm using a solid tool here. So this tool has been modelled in the CAD functionality to accurately represent exactly what I'm using on the machine. So any collision potential or gouging is very, very accurate. We can snap to different portions of the toolpath, so we can analyse this toolpath quite nicely. Okay, so I just want to talk about barrel cutters. So barrel cutters have been around for quite some time now, particularly in aerospace and defence type of areas. However, they are now getting more mainstream. So just a quick recap on barrel cutters, what the benefits are and what they're good at. Barrel cutting tools are used for various machining operations, including finishing of flat or slightly curved walls. Typically, because of the shape of the barrel tool, you can get at least the same, if not better, surface finish with a much bigger step down than you would a standard ball nose. And as a result, see up to 3 times or more decrease in the machining time. This is particularly true when doing semi-finishing, where you can have a really large step down. I think this image on the PowerPoint displays that nicely. So I've got this example of this particular part. This is an aerospace bracket. I've roughed it out using a standard adaptive milling operation. And the first operation is a fairly standard variable contour operation. If we just display that toolpath and if we replay that, you can see that this is a barrel cutter and you can see it's following the profile around there. And I've got a fairly aggressive step down, and because of that, because of the barrel cutter, I can still get a good finish using that aggressive step down. As an example, or as a way of seeing the difference, I've also created a fairly standard 5-axis Z-level operation, but this time using a ball nose cutter. I've used a similar step down just so we can compare the differences. And again, if I replay this, you'll see that this is obviously a ball nose cutter with, again, the fairly aggressive step down. I'm going to use our analyze operation to just have a look at the different surface finishes that we're getting with those 2 different types of cutters. So you can see this is a colour-coded analysis tool that shows us the material status, and you can obviously define the different gradients yourself. So if we look at the pocket where we've used a barrel cutter, that's a fairly good finish, and you know, we could improve on that, I guess, by decreasing the step down slightly, but that's fairly acceptable. Whereas using the ball nose cutter with the same step down, you can obviously see the scallops, and you can see the issue we're going to have there. If we click on one of those scallops, you'll be able to see that we're obviously leaving a lot more material in those areas than we should be, than we would be with the barrel cutter. So that's a nice way of just identifying the different surface finishes using the analyze tool. During my earlier introduction, I mentioned the need to go from 3 to 5-axis machining very easily. When dealing with deep cavities, a 3-axis toolpath will be very limited because of the collision potential with the holder. What NXCAM will allow you to do excuse me, is program in 3-axis, and the system will constantly look ahead for tool holder collision. When none is encountered, a 3-axis toolpath is output. When we see a potential collision, the tool axis is gradually tilted away from the collision area, resulting in a 5-axis toolpath. As you can imagine, this is a very popular and efficient feature in the mould and die industry. The functionality is also extremely useful for companies moving from 3 to 5-axis machines. So in this example, I've got a fixed axis guiding curve operation. So this has been created using the fixed axis module. And if we look at that, we can see I've created just a simple toolpath to machine down the walls of this particular pocket. If we look at that in verify mode, and if we look at the tool position at the top of the pocket, you can see everything's fine, no collision potential. But as we move down towards the bottom of the pocket, you can see I've got collisions there. Now, I've actually turned off the gouge check-in on this particular operation just so I can show you what would happen there. So obviously with a fixed axis, we would either have to extend the tool a lot longer, and obviously that causes issues in itself. Just to show you an example, if I just quickly hit the gouge check on that and say OK, you can see that it's showing me that that toolpath is creating gouges. Once it gets to a certain level, it's showing these gouges, and we get this toolpath report showing us all the detail of that. What I'm going to do then, I'm going to automatically convert that from a fixed axis toolpath to a multi-axis toolpath. And I can do this either inside or outside of the operation, but we'll go inside the operation itself. And under the avoidance, we can change that to tilt and retract. Even though this is a 3-axis toolpath, we can still do this. And we can set up the variables, so minimum and maximum tilt angles, clearances, that type of thing. I'll accept the defaults, OK that, and generate the toolpath. OK, if we now verify that toolpath, what we'll see is at the top, again, not too much collision potential, but as we get down towards the bottom, you can see NX has tilted that tool over so that there is no collision potential. And so what that's done is it's automatically converted a fixed axis operation into a multi-axis operation. So that means that if you've got an existing operation on a fixed axis machine, a 3-axis machine, and you want to put it onto a 5-axis machine, you don't have to reprogram the part. You can just automatically convert to multi-axis toolpaths. A recent addition in NX of rough tube and finish tube operations allows us to quickly program complex shapes such as ports, intakes, etc. We have a choice of machining side, crossover points. The tool axis is again handled automatically to decrease programming time and provide the best tool axis solution. As we've previously seen, the need for true G-code machine simulation on these types of toolpaths is essential. We'll take a look at NXCAM's internal simulation package again, and at the same time look at the tube machining. So here we've got the cylinder head on the same machine. Again, let's just quickly hide the machine temporarily, and we'll look at these operations. So we've got roughing operations, tube rough, and in this case I've programmed an operation that comes from one side of the feature and machines down to roughly halfway down the feature. And then I've taken the same type of operation, but this time I'm machining from the opposite direction, what we call the exit direction, and again to approximately midpoint of the feature. And that's acceptable, breaking it into two different toolpaths. But what we can do also is we can create one toolpath that attacks from both sides. So it will machine from the entry side down to a specified point. That could be 50% or it could have an overlap. And then it will come around and machine from the exit side. So you're roughing the whole feature out in one toolpath, in one operation. And then I've done the same again on the opposite feature. I've created a tube finish operation. The tube finish operations are very similar to the tube roughing operations, the only difference really being the toolpath pattern, because obviously we're now finishing. So if we look at the tube finish operation, you can see if I zoom in there, it's a sort of profiling type operation. In this case, I'm helically profiling around that feature. And you can see, again, I'm machining from both sides, from the entry side and the exit side, and meeting at some point in the middle. And similarly with the opposite side. So again, this type of toolpath on this type of component, it's really essential that we prove these out offline before we go onto the shop floor. So if I switch the machine back on and we go into the machine simulation area of NX, so again we can see the post-process program. We can see the machine status again if we choose to, and we can start to run the G&M code so that we're proving out offline. So let's press play, and you can see the tool comes in and starts the machine. I can display the tool trace so I can then see the toolpath that's being created. Sometimes that's helpful. You can see the machines moving around quite a lot, so this is why this type of toolpath really needs this offline prove out. Okay, let's stop that. The NX Turbo Machinery module, it's been available for quite a few versions of NX. It's a specific module that's specially created for complex blade type components. It optimises the programming of these 5-axis parts such as impellers, blades, blisks and so on. Again, using automation where necessary to control the tool axis and the cutting strategies, so you can get quick, efficient toolpaths. The turbo machinery functionality has been developed over the versions to keep pace with the complex and different ways of machining these types of parts. One of those enhancements is the addition of multiple stripe cut level support. This allows for the precise blending and division of multiple toolpaths on these turbo machinery blades. It's a great aid when cutting long, thin-walled blades where the milling of material needs to be broken into steps. The stripe cut levels feature allows the toolpath of the blade to be broken into top, intermediate and bottom sections. These can then be independently controlled and seamlessly blended between different cutting operations. Another announcement has been the addition of toolpath support for the tangent barrel tools. So with the addition of this tangent barrel tool support, blades and other spline curved walls can now be machined much faster. We also have the ability to adjust the amount of stock material left behind different areas of the blade. So therefore precise control of stock removal can be achieved. Let's look at that multiple stripes. So I've got this blisk and I've roughed it out. I've created a roughing operation to rough between the two blisks there, and then I've transformed that operation associatively to machine the rest of the component. I've then created a blade finish operation, and you can see this is machining from top to bottom on that particular blade. Let's have a look at that. So this is a typical blisk blade finish operation. You can see we can define which sides of the blade to cut. We can define how the depth mode works. Does it interpolate from the shroud or the hub? And obviously the depth per cut and so on. We're using a helical cut pattern. Now the range type, instead of changing it, leaving it at automatic, we've got this multi-stripes option. So if I define multi-stripes as a range type, I can then say top, intermediate or bottom. So let's say top, and let's say we start from the top and we go to, I don't know, let's say 30% of the depth of the blade. If I regenerate that, we can see that we now just have the toolpath at the top of the blade. And so the principle with this would be that we would accept this operation, we would then copy it, and then in the copy we would change the stripe type from top to intermediate or possibly bottom, and we would then define the percentages and regenerate. So we can control the levels of the blade quite accurately. The ability to merge paths is a recent enhancement that allows us to combine two or more operations into a single operation to improve machine efficiency. You can combine these operations using the Operation Navigator in NX and the Create Program dialog box. The operations that you merge must all use the same tool. So this is an example where I've got this thin-walled feature, and the reality is if we rough this out and then semi-finish and then finish, we often get the situation where these thin walls tend to distort or bend, and it can be quite a problem. We can waterline machine, we've always been able to do that inside of NX, but in this case we're going to use the merge paths functionality to achieve what we need to on there. So I've got a semi-finishing operation using a ball nose cutter, machining down fairly aggressive depths of cuts, and it's leaving 1/2 mil stock on for finishing. And then we've got the finishing operation itself, again using the ball nose cutter, obviously not so aggressive step down and leaving 0 stock to finish that component. So I want to merge these two toolpaths together because I want it to cut so far down with the semi-finisher and then finish, and then carry on with the semi-finish and then finish, and so on and so on. So under my Create program, under Mill Multiaxis, I've got this merge path option. So if I OK that, I can now define how we merge these paths. Concatenation is one option, and the little diagram there shows you what that's going to do. And we've also got by contour count. And what I'm going to do with this, I'm going to say the first semi-finishing pass is going to do 5 passes, and I'm going to add that to the list. And then the finishing pass is going to do 10 passes, and I'm going to just apply a little bit of lag there. I don't want the finishing to go all the way up to the semi-finishing, so I'm going to apply a little bit of lag. And let's say 2 there. And so if I say add new set onto that, oops, should have changed that, accepted that before. Right, so we've got 5 and 10. Okay, that. So this is created like a subfolder, if you like. And I'm going to drag the two operations into that subfolder, and I'm then going to generate. So if we now verify this, what we should see is, if just slow that down a little bit so we can see what's happening. So we've got the semi-finishing pass, and that will do so many passes around, 5 passes around that profile. And then we get the finishing pass, and that will go down so far. As I said, I've applied a lag of 2 to the finishing pass. So now we get the semi-finishing pass again, and again that will go down those 5 passes before changing to the finishing pass, which will then go down to catch up with the semi-finishing, and so on and so on. So you can see, you know, we could have done this in a very long-winded way before, but this is really quite nice using these new merge path functionality. Although not technically multi-axis, I just want to mention a new probing functionality that has been created and provided exclusively by OnePLM. This has been created to be a usable solution for a CNC programmer stroke production engineer. It uses exactly the same dialog boxes and tooltips that the NX CAM user has become accustomed to. OnePLM will also provide post-processor support to output the probing cycles in the correct format that your machine expects to see. There will be more information about this at the end, and we'll be running a specific webinar based on this functionality. So to sum up, as you're all aware, complex part machining requires more than just 5-axis techniques. To be productive, you need a comprehensive suite of programming capabilities, such as 3-axis milling, turning, hole making, feature-based machining, and machine and G-code simulation. You also need the ability to control and manage your tooling, your fixturing, and your shop floor documentation. So this is why the NXCAM system has been adopted across many industries, delivering proven manufacturing capability from aerospace to medical, from mould and die to power generation, and many, many more. The development speed from Siemens over the last few years has set the pace for multi-axis CAM software. Take a look at the very latest versions of NX. They'll seem a million miles away from the older versions. So thank you for your attention, and I'll hand you back to Lee.
Thanks for that, Mark. So that concludes our webinar for today. A recording of the event will be made available, so if you wish to receive this, please get in touch and this can be emailed across to you. Also, if you require anything further, you can reach out to me via my mobile or alternatively my email. Again, thanks for your attendance today and enjoy the rest of your day.